Hello and welcome to CSE 373, Section 5. In this section video, we'll be reviewing heaps from last week. We won't be doing any midterm review just because by the time you're watching this, you will already have taken the midterm. For our agenda, we'll be going over some course announcements and then spending the rest of the time on reviewing heaps. For course announcements, P2 closes on Saturday, so make sure to get that in if you have not already. And even if you're still working on it and won't be done by the time 11:59 comes around on Saturday, please turn in what you have just so you can maximize points. And then exercise 4 is due on Monday, May 1st, with a late due date of Thursday the 4th. And midterm resubmissions come out Wednesday the 3rd, so keep a lookout for that, where you'll be able to resubmit questions you lost points on to get up to half of the points back that you missed. Let's jump into some heaps. To review some terminology, heaps are complete binary trees that maintain some heap ordering or heap ordering invariant. As a reminder, complete binary trees are binary trees where every level is either completely filled, or if a level is not filled, all nodes are in the leftmost position. So you can kind of think about it like building a binary tree level by level, left to right, where all on the lowest level that may or may not be filled, all nodes are contained in the leftmost position. And for the heap ordering, this will change whether we're working with a min heap or a max heap. Essentially, it states that a parent node's value must either be less than its child nodes if we're working with a min heap, or greater than both of its child nodes if we're working with a max heap. And we can see an example of a min heap to the left over here on the slide, where the parent node's value is less than both of its child nodes. We will be reviewing the following operations: removeMin / removeMax, depending on if we're working with a min heap or a max heap, which removes the root node of a tree and then replaces it with its last child node, where we will do some percolating to fix the heap ordering invariant if it was violated. And then we also have inserts, which is another common heap runtime or a heap operation. And these operations both run in O of log n, and we'll see later on that this is because we have to do maximum log n percolations when performing these operations. For inserts, if we were to insert 7 into this min heap, we would insert at the very last leaf position because we're working with complete trees here. And as we can see, once we inserted 7 into the last leaf position or the leftmost leaf position, our heap ordering invariant is now violated because this 7's parent is greater than 7, which should never be the case in a min heap. So this means we'll have to flip these two in order to restore the heap ordering invariant. For removing min, if we were to remove the overall root node of our heap, or this 2, we would insert it with the last child node. And then we would have to percolate down in order to restore our heap ordering invariant. Because as we can see, the 7, or the previous last child, is now greater than both of its children. So we're going to have to do some percolating to restore our heap ordering. Great. The underlying representation we will use for heaps is an array, where this is an example of an array representation that starts at index 1. And if you compare the array representation with our tree diagram on the right over here, we can see that we essentially go level by level, left to right, and inserting all of the nodes into our array. So starting with 1, we see that 1's contained at index 1, this 54 is at index 2, this 3 is at index 3, and so on and so forth. And the reason why we use this representation is because now we have some very convenient ways to access parent and child nodes. So if a node is located at index I, we can jump to its left child, or because we know it's at index 2 times I. It follows that its right child will also be at index 2i plus 1. And if we want to find the parent of a node located at index I, we can just divide that current node's index by 2, and then chop off the decimal point or take the floor. Think about it like performing Java's truncating division, on the index when dividing it by 2. But what if we didn't want our array to start at 1? Instead, start at 0, because it's like more natural for us to work with, I guess. If this were the case, it's nice because now our array starts at index 0, but our math gets a tad more messier. Now we have to add, our left child would be located at index 2i plus 1 instead of just 2i. Our right child would be located at 2i plus 2. And now to find the parent index, we would have to subtract 1 from I before dividing by 2 and taking the floor of that, or removing the decimal point from the quotients. Cool. Now let's pause the video, and I want you to attempt problem 1A through D. This will walk you through creating an array representation of a ternary heap, so a heap where every node can have up to 3 children, and then doing some math and coming up with the formulas for the new ternary heap instead of a binary heap. So pause the video and attempt problems 1A through D here. All right, let's walk through this problem. So we want to insert these values into a tree representation of a heap. Because our heap was empty before, we can add 5 as the overall root and be fine. Now we insert 20, 10, and 6 in the last child positions, or the leftmost leaf positions. And since none of these values are less than 5, our heap ordering is maintained, and we're good. Now if we were to insert 7 into the last leaf position, we have violated our heap ordering property because 20 is not less than 7. So we have to percolate up and flip these two nodes. And boom, now our heap ordering invariance restored. Now we want to insert 3. And once again, our ordering is violated because 7 is not less than 3. So we have to percolate up and flip the values of these two nodes. And now we notice that our heap ordering is still not restored because 5 is not less than 3. So we need to percolate up one more time and flip the values of these two nodes. Great. Now if we were to insert 1, we would have to perform the same two operations that we just did with 3, because 1 is less than both of its ancestor nodes. And finally, if we were to insert 2, we'd only have to percolate up once, because 1 is less than 2. Now, suppose we wanted to turn this tree representation into our array representation of this heap. If that were the case, we just have to go level by level, left to right, inserting nodes into our array. So 1 would go in the 0th index, 3 would go in the first index, 2 would go in the second index, and so on and so forth, until we've added every single index or value to our array. I'm going to move my camera. Oh, great. So now, given a node at index I, what's the formula to find the index of that parent? And then this is the formula for a binary or 2 heap. Well, just looking at it, we notice that there's a 2 here, and this is the formula for a binary heap. So what if we just pattern match and replace this 2 with a 3 and keep everything else the same? That seems like a valid approach to coming up with this formula. And if we do this, it will work. And just to verify, we can run through indices 1, 2, and 3 and verify that they all map to the 0 index. And to go one step farther, I'd also run this formula on index 4 to make sure it does not map to index 0, but in fact maps to index 1. And we see that this works. And we can perform the same pattern matching for the other formula as well. So in our binary heap, if our left child was located at 2i plus 1, and our right child was located at 2i plus 2, what if we just replace these 2's with a 3? And this will work as well, where our left child is located at 3i plus 1. Our middle child, since we're working with a ternary heap, is located at index 3i plus 2. And the rightmost child is located at 3i plus 3. We just have one more child to take care of, which will be located one index past the middle child. Great. Now pause the video and attempt problem 2E, removeMin. All right, I'm going to assume you attempted this problem, and now let's go over the solution. So suppose we wanted to call removeMin on this following min heap. If this were the case, we would remove the 2 node and replace it with its last leaf node, which is the 9. But once we do this, we notice the heap invariant, or the heap ordering invariant, is broken. So we need to percolate down and swap 9 with one of its child nodes. But which child node do we swap with? Well, we should always swap with the minimum child. If we swap with a non-minimum child, then we're at risk of our heap ordering invariant still being broken. Like in this case, if we were to swap with 9, and if we were to swap 9 with 7, instead of 9 with 5, 7 would then become the overall roots. However, 7 is still greater than 5, so our heap ordering invariant would still be broken. So thus is why we have to swap with the min child. So once we do this, we notice that our heap ordering is still broken because 8 is less than 9. So we need to percolate down and swap one more time. And that's this entire problem. Great. Let's move on to problems 3A through C. So pause this video and attempt problem 3. Great. Let's walk through this. So 3A asked you, suppose you have an array representation of a heap. Must the array be sorted? The answer is no, right? Like in the last problem, the child nodes may or may not be greater than one another. So if any of the child nodes are not in the correct sorted order, then this would disprove the statement. And we can see that here, where this heap is 1, 2, and 5. And then 2's child is 3, which is not a sorted array, but is a valid heap. All right, problem 3 asks you, suppose you have a sorted array in increasing order, so 1, 2, 3, 4, 5, etc. Must it be the array representation of a valid min heap? Well, if our array is sorted, then we know for sure every earlier index is going to contain a value that's less than later indices. So this must be true, where a sorted array in increasing order will always be a valid min heap, and the heap ordering invariant is maintained. All right, for problem 3C, you are asked, you have an array of representation of a min heap. If you reverse the array, does it become an array representation of a max heap? And the answer is no, right? It once again has to do with the children being in different order. So if we were to flip this, right, then because 5 was an immediate child of the previous overall root 1, then we can see that this would not be a valid max heap, and the statement is not true. Oh, and one thing I'd want to add in this video is the runtime of heap operations. Like what appeared in a few slides back, inserting and removing min are both log n operations. This is because those runtimes are dependent on the number of percolations or swaps we have to do whenever we insert a node or remove a min or max node. Well, the maximum number of percolations will be the height of our tree. And because heaps are complete trees, the height is bounded by log n. So that's why those runtimes for those operations are both log n. And then one more common heap operation would be like peak, or peaking at the min or max value. This is constant since we can just jump to the earliest index in our array. All right, that's everything. And yeah, have a great weekend, y'all.